I think by now you should have a fair understanding on the quantum mechanical property of the qubits and how it differs from classical objects. Yeah. So Claire have said that in his lecture that the quantum mechanics will become weirder if we consider more qubits. And in these lectures, we will see like how a more peculiar quantum effects like quantum entanglements emerges from the mathematical structures of like canonical products and the principle of superpositions. Yeah. So okay, this is the outlines of today's lectures. So I will first lay out the basics uh, behind two qubit systems. So I will first introduce the mathematical structures of two qubit quantum system, then the operations that act on two qubit quantum system. Then with all of the basics introduced, we will go into like the quantum entanglements, and then like the quantum teleportations, like one of the applications of entangled quantum states. Yeah, let's start off with mathematical structures of two qubit quantum states. So similar to previous two lectures, we will just focusing on the qubits. No qubits is involved, like more than two level systems. And then what we consider here is the pure sets, which there's no classical uncertainties. Then, yeah, and we also focus only on two qubit systems, and this is sufficient for our studies. And you could also have like more than two qubits, and there's also entanglements between these qubits, but it will be much more complicated, and there are some like many body physics, many body phenomena that comes into play. Yeah, but here we will be just focusing on the qubit systems. So now you already know like for qubits, you could describe it using like the computer describe the quantum state in terms of like computational physics. And let's now imagine that you have two qubits. One placed at CQT NTU and the other placed at CQT NUS. Yeah. So each of these qubits could have their own computational basis that describe their states. The question now is then, how do you describe these systems as a whole, right? Then you need some mathematical structures that combine these two systems, and then you have to apply all the bond rule, and so that you have to extend the notion of bond rule to these multi-qubit systems. And yeah, so actually, you guys have learned the mathematical operations yesterday on the linear algebra lectures, which the canonical products. So here we'll be using this canonical product to combine to form to construct a bigger space that describe the quantum state of two qubit systems. For example, consider here that you have the qubit in NTU in zero state as well as the qubit in NUS. Then basically their state could be described by cat0 and the same for NUS. So to describe the system as a whole, then you make use of tensor products to combine these the cat0 at NTU and the cat0 and NUS. Indeed, you could have like different kind of combinations, like 0, 0 in NTU, NUS, 0 in NTU, 1 in NUS, 1 in NTU, 0 in NUS, and 1, 1 in both NTU and NUS. Yeah, so you could see here we have different kind of combinations, and you could see that here the notation is a bit like complicated, or if you want to write an equation for it, if we keep like including this tensor product, this and label, then it'll be kind of like a bit messy if you want to do the calculations. So for some of the calculation, I will use some simplified notations where we always like, so this notation goes like this. Each of the qubits, we label the qubits by their sequence. So for example, the NTU will always come in the first qubit, and US will always come to the second qubit, and this will be the simplified notations. By using these simplified notations, we could see that this is our computational basis for 2-qubit systems. So similar to single qubit systems, all of these bases will be orthogonal to each other's, and you could verify using either the Dirac notation or the vector representation of it. Then to construct the arbitrary 2-qubit states, right? Basically, we could just invoke the principle of superpositions to combine all these bases by using some coefficients, alpha, beta, gamma, and sigma, and these coefficients are complex, and they have to respect these equations, which say that we need to have the sum of the probability to be equal to 1. We will look into this in more details, or mathematically, we could write the general quantum state in this form. Yeah, so for this quantum state, it is 4-dimensional vectors, and it will be clear if once we goes into the vector representation of it. Yeah. So how if now we have a general quantum states in both NTU and NUS, and is the state is this and this for. Similarly, basically, we just apply the tensor products to combine these two quantum states, and then we just expand the quantum states to this. So basically, these tensor products in Dirac representations, the operation is kind of similar to the multiplications. For example, now what we have done is just like cross multiply each of the term between these two round brackets. So 0 multiplied with 0, and the coefficient is a times c, and 0 to 1, the coefficient is a times d, and so on and so forth. Yeah. Then we simplify the notations, and this is what we got. Yeah. So if we compare with the previous expressions, which is shown here, basically we could see that these two expressions like is equilibriums. It is the same if alpha equal to AC, beta equal to AD, gamma equal to BC, and sigma equal to BD. However, like this relation cannot be found for entangled quantum states. Yeah. So we will be going to this. So please keep in mind about this, and we will go into more details later on in part 3. I remember part 3 of the lectures. Yeah, you could see here. Basically, what the conical product does is just combine 2-dimensional complex vectors into one 4-dimensional complex vector. Yeah. To see more clearly, we have to go into vector representation of it. So recall from yesterday lectures, if we have two complex vectors, and if we apply we find the conical product between these two vectors will be something like this. So you treat A and B as the scalars, and then you multiply the vectors of it, then this will be the conical products of these two complex vectors. Yeah. So you could see that this conical products combines two complex vectors into one two-dimensional complex vector into one 4-dimensions complex vectors, allowing us to describe the quantum systems using these vector representations. So let's apply this to our computational basis. Recall that the computation basis for single qubits is this 0 and 1, and is represented by 1, 0 and 0, 1 vectors. So if we do the math, then the vector representation of the computational basis for 2-qubit systems will be something like this. Yeah, let's do some example. Now we just compute compute the vector representation for 0, 0 state. What we have here is this. So we have this is 0. This is the vector representation of 0, 0. Then basically we just did do this kind of operation, and this is what we got, which agree with this these equations. Yeah. So in the exercise, basically I left all of this for the exercise for you to verify the rest of the tree. Yeah, it's quite simple as the math is quite simple. You could do it like based using following this example. So now we have this vector representation of the computation basis. Then that means we could just find the vector representations of the arbitrary, like the general quantum state for two qubit systems. Yeah, so for two qubit system is something like this, and this alpha, beta, gamma, and sigma, it has to respect the sum of unities. Okay, so now we know how to describe our two qubit systems. How if now we want to perform measurements, and what will be the measurement outcomes, and what would be the probability of getting some measurement outcome? So here we could extend the bond rule to two qubit systems, and the bond rule give us the statistic of measurement result of two qubit states. Yeah. So to continue on, we have to introduce some tool. Actually, it should yeah. So you previously in previous lectures, you have seen that the inner products and Hermitian conjugate. Yeah. So now we want to extend this to two qubit systems. How do we apply this kind of operation in two qubit systems? Yeah. So this will be the operations and the rule of thumb is that each of the first part of the Dirac, this bra will only meet with the first part of the head, and the second part of the bra will meet with the second part of the head, and then you multiply both inner product together. Yeah. So similar for the Hermitian conjugate, you apply it individually, and then eventually you get this. And one of the important things that have to take note is that this Hermitian conjugate wouldn't change the orders of your qubits. Yeah. So before you take the Hermitian conjugate, NTU is in the front, NUS is at the back. And after the Hermitian conjugate, you also need to have the NTU, the head NTU, the bra NTU in France and bra NUS at the end. Yeah. Then after we know all it's true, then we could calculate the probability of getting outcome of phi using if we are given quantum state phi using the bond rule. So yeah, it's pretty similar to the case with one qubit system. And for vector representation, you just need to take the inner products of take the dot products of these two vectors. And then for this, we will go into this example to see how we could evaluate this guy. So let's do some example. Here, what we are interested is to find the probability of getting 0, 0 state from this phi plus. So this phi plus is defined by this. Oh, sorry. So yeah, the Dirac representation of this phi plus is this guy. So it's 1 over square root 2, 0, 0 plus 1 over square root 2, 1, 1. Yeah, so we apply the bond rule to find these probabilities, and we just expand these terms. Then from the inner product, we know that this first zero will meet with this first zero, and second zero will meet with second zero, and we multiply the inner product of both together. The same go to this one. 0 with meet with 1, and 0 with meet with 1 is this one. Yeah. So here, actually, from your knowledge of single qubit system, you know that this 0, 0 is the inner product of 0, 0 is 1, where the inner product of 0 and 1 is 0 because they are orthogonal to each other. So at the end, what you got is that the probability of getting 0, 0 from phi plus is half. Similarly, you could do it using the vector representations, where you just need to find the inner product between the two and you get the same results. So you could see that here the Dirac representations and the vector representations give us the same results, showing us the consistencies of these formalisms. Yeah. Then, okay, so now we have this Bond's rule, right? We could apply to the general quantum state that we defined just now. So what we want here is to find the measurement outcome of this psi totals in the computational basis. Yeah. So you apply the Bond rules, and then you basically found that it's just the mod square of the probability of finding 0, 0 given this state is alpha square. Probability of getting 0, 1 is beta square, and so on and so forth. So here you could see that we could interpret alpha, beta, gamma, and sigma as the probability amplitudes that will give us the probabilities of getting each of the basis, getting each of the basis after measurements by calculating their mod square. Yeah, because the probability need to be conserved. We need to have these equations in order to emphasize that the probability of getting like either 0, 0, 0, 1, or 1, 0, or 1, 1 will be unity. Otherwise, we are doing something wrong here. Yeah. So far, we have been talking about the measurements on 2-qubit systems, right? Can we just, by using this formalism, can we just like measure the first qubits and will this like give us the correct statistics? Yeah. For this simple quantum states, you could see that like by doing some mathematics, and this is in the lectures, but I wouldn't show it here. But here, what I want to show here is that this tensor product structure to give us the correct single qubits measurement statistics. And then the other things that I want to mention here is that for this quantum states, the measurement outcome on the first qubits wouldn't affect the measurement outcome of the second qubits. Yeah. So this agree with our common sense, and it makes sense to have the measurements results of different qubits to be independent to each others. But there's one class of quantum state that behave in a different way, where we will see it later for this entangled quantum state. The measurement outcome of one qubit will depend on the measurement outcome of the other qubits. Yeah. So here there are two things that I left for later part lecture. The first one is the separabilities of the quantum state. The second one is this one, the dependence of the measurement outcome between like two qubits. So now we have, so we have all the basics for how to describe the 2-qubit systems and how to find the measurement outcome of these 2-qubit systems using Bond's rules. And now we have to find a way to combine the quantum operations so that we could have a like consistent way of describing the quantum operation for 2-qubit systems. Now, let's consider this. For example, this is your qubits in NTU, and this is your qubit in NUS. For each of the qubit, you have the corresponding quantum operation that acts on it. The question now is that how do we construct the joint quantum operation that act on this joint quantum state? Yeah, and actually, you have learned that the quantum operations O NTU and O NUS can be represented by 2x2 matrix, since the qubit space is two-dimensional. Yeah, and previously we have seen that for 2-qubit quantum states, it could be described by a four-dimensional vectors. This means that this quantum operation has to be also be represented by 4 by 4 matrix in order for the dimensions to be consistent. Yeah, this kind of give a hint to like to find operation that could combine these two operation into one big operation that act on the larger space. Yeah, so it's not surprising. It's still a tensor product. So so this will be the definitions. This O total is the joint quantum operation that would act on the joint quantum states. And yeah, so basically you just like find the tensor product between these two operators. For example, if your operators can be described, can be represented by these two metrics, then the canonical products of these two quantum operations will be something like this. Yeah, so here what I have like, basically this should like give you should recall something, because this actually is in this equation actually introduced in previous lectures on linear algebra. So what I did here is just like linked the physical systems with the mathematical abstract. Yeah. Then yeah, so we could also find the Hermitian conjugates of the operations, and it's given by this. Yeah, I have an exercise for you to verify this, but it should be quite easy, quite straightforward to do the verifications. Yeah. Okay. So we have these quantum operations. Then yeah. So with these quantum operations, we could use it to so there's one class of this quantum operations is the unitary operations, as introduced by Clive in these lectures. So basically what these unitary operations does is just to evolve the quantum states, right? So in these two qubit system, you also have the unitary operations. Then it also preserves the norm of the two qubit quantum states. So for example, if we have this unitary operation for the lab in NTU and for the lab in NUS, then the joint unitary operation will be something like this. The unitarity of these joint unitary operators will be following immediately from these definitions. Like, let's like work it out. So here, this one basically I just multiply the complex conjugate, the Hermitian conjugate of the unitary with the unitary, and then I expand out the equations. So so similar to the quantum states, the operators in the first part we only meet with the first part, and second part we meet with the second part, and this will what you get. And from this unitarity of each of the individual unitaries, then we could like kind of see that it is equal to identities, and the tensor product of two-dimensional identities is one four-dimensional identity. So I labeled the subscript 4 here is labeled the dimensions, and without subscript, basically I just like say it is two-dimensional identities. Yeah. Okay. Yeah. So now we have introduced the quantum operations, right? And now we will see what is the actions of these two quantum operations on the joint quantum states. So so here this will be our joint quantum operation, and this is our joint quantum states. Then similar to previous two cases, the quantum operation in the first part only meet with the quantum state in the first part, and the same for the second part. So the quantum, basically all of this, like for tensor product structures, basically when you are finding inner products, like quantum operation acting on some quantum states is operating in a slot by slot basis. So the first slot meet with the first slot, second slot meet with the second slot. Yeah. This is good because it allows us to describe a spatial spatial condition. For example, if you want to have the qubits in NTU, like you want to do anything on the qubits in NTU, but you want to do some operations in the for the qubits in NUS. Yeah. So this will be the operations. The identity stand for you are doing nothing, and then we are applying. So it's acting in a slot by slot basis, and these identities will just do nothings on the quantum state. Is what we get. Yeah. So this is important because it's kind of give us some freedoms on what kind of operation that we want to perform in each of the labs. And yeah, okay. So this will be the actions of quantum operations. Then, okay, yeah. So what we have been introduced so far is how to describe the quantum state of two-qubit systems and how to perform the measurements and what the measurement outcome of the quantum systems. Then we find the way to describe the joint quantum operations that act on the quantum states. Yeah, and then we look into how to perform the quantum operation on two quantum states. Yeah, so all of this basics is requires to understand the following sections, and this will be the main part of the lectures, which now we'll be studying in details on the quantum entanglement. Yeah. So recall the combination basis is given by 0, 0, 0, 1, 1, 0, and 1, 1. Then we could construct a general two-qubit quantum system by invoking the principle of superpositions, and alpha, beta, and gamma, sigma need to respect the mode square of each of these the sum of mode square of each of these coefficient need to be equal to 1. Yeah. So this means that the quantum state will have to be normalized. Therefore, we can kind of define this quantum state. This is one of the Bell state that we'll see later on. Yeah. So we could define this state by letting alpha equal to 1 over square root 2 and sigma equal to 1 over square root 2. So this is fine because the quantum states are normalized where the mod square of each of this is equal to 1. Yeah. Now imagine that Alice and Bob. So you can imagine Alice staying at the lab in NTU, Bob staying the lab in NUS, and each of them hold one of qubits from this Bell state. Yeah. Then now, for example, if Alice measures her qubits, then what she will get is just 50% of this state. This is 0, 0 because this is the polar circles and this line is the 0 axis, and this one is 1, 1. So if Alice measures her qubits while Bob did nothing, then she will get 50% of this quantum state and 50% of this quantum state. If after Alice measurements, then Bob measures his qubits, sorry. Yeah, then actually Bob will find that his measurement if he compare his measurements outcome with Alice measurements outcomes in computational basis, he will find that his measurement outcome will always aligned with Alice outcome. For example, if Alice measures 0 state, then Bob will always measure 0 state if both of them measure in computational basis. This is the same for the case of this. If Alice measures Kate 1, then Bob will also measure cont'd. This observation is kind of strange and peculiar because it seems like Alice's measurements has forced the Bob's qubits to choose the state that's aligned with Alice's state. Yeah. So this effect is still exists even if these two qubits are separate by a vast distance. For example, if Alice's qubit is placed on Earth, while both qubit is placed on Alpha Centauri, there's like 4.367 light years away from Earth. This effect is still perceived. Yeah. So it's kind of weird, and yeah, so this kind of link to all the familiar term that you hear from the pop science. Like this is this what Einstein called the spooky action at a distance, because it seems like one qubit immediately knows the outcomes of the other qubits, appearing like to be transmitting information faster than the speed of light. And for Albert Einstein is like absurd because this violating his like theory of relativity. But actually this wouldn't like this there's no contradiction here because no information is actually transmitted between these two qubits. Yeah. So in order for Bob to do this kind of comparisons, Bob need to know like what basis Alice measures her qubits on and when Alice measures her qubits. So if Bob doesn't know like all of this information, basically from his perspective, the qubit will appear to be randoms. So even if Alice measures her qubits, this wouldn't change this fact. Yeah, if this involves some more advanced concept called density metric in order to see that the quantum operations on the Alice side wouldn't affect the quantum the state on qubit sides. And yeah, this need to be this has to use density metrics formalism in order to describe this. Yeah, but just one of so the take home message for this is there's no information that's transmitting between the two. Yeah, and if Alice send her measurement outcome to Bob through classical channel, and this is limited by the speed of light. Yeah, so there's no violations of there's no faster than light communications in short. Yeah. But actually, there's not all the quantum state that has these peculiar properties. Like let's consider this state. So for this state, basically, you could separate into two parts. This first part stands for the qubit. There's the quantum state that describe the qubits, Alice qubits, and this is a quantum state describe Bob's qubits. Yeah, you could see if Alice do measurements, basically she always gets like 0 K from her outcome, and for Bob, he will get 50-50 like there's a 50-50 chance of getting zeros and 1 for getting 0 and 1. Yeah. So and this happens in respect to like the measurement sequence of these two measurement sequence of Alice and Bob. Yeah. Mathematically, it could be written in something like this. So you could see that this is cat 0 and this is a linear superposition of 0 and 1. Yeah. Yeah. Okay. So this kind of state is called separable quantum state. Yeah. So for this separable quantum state, the actions of one qubit wouldn't affect the actions of the other qubit as long as the quantum operation is not entangling operations. Yeah. So let's go back to the Bell state. Now I just want to show that this Bell state couldn't be written in this form. Yeah, into like cannot be written in psi1 tensor psi2, which we have in previous page. Yeah. So, okay, we can do this, we can prove this by contradictions. So let's assume that this Bell state can be written as a tensor product of two separate two-qubit states. And this will be, so this left-hand side, this will be the vector representation of this guy. And this is the vector representation of the Bell state. If we compare the second entry, we have AD equal to 0. This implies that A equal to 0 or D equal to 0. Yeah. Then this means that AC must be equal to 0 because if A equal to 0, AC must be equal to 0. Or if D equal to 0, then BD equal to 0. Yeah. But this is not the case because here we have, for this Bell state, we have AC equal to BD equal to 1 over square 2. This kind of like contradict each other. So we can conclude that this Bell state couldn't be written in the tensor product of two single qubits quantum states. Yeah. Okay. So this is all mathematics, but let's give some like insights on this. So what this means is that all qubits in the entangled system should be treated as one entity. So you couldn't like, if a state couldn't be written as the tensor product of two single qubit quantum states, then we are not able to describe it. So we need, okay, sorry. So if we cannot like separate the two qubit system into the tensor canonical products of two single qubit states, that means we have to describe these systems as a whole. And for this kind of systems, the measurement statistic of both qubit will only be meaningful only if they are compared against each others. Like for example, if you measures this state in computation basis for the first qubit, and you have to compare against the measurements results of the second qubits for the combination basis. Only then you will find that their measurement results align to each others. Yeah. So this kind of quantum states are called entangled quantum states, and is this kind of quantum state that contain the exotic quantum mechanical resources, like the quantum entanglement that you guys hear most in internet. Yeah. So this quantum entanglement is one of the important quantum mechanical property that has huge impact on quantum information in quantum technologies. You could see this like quantum entanglements from in many areas. For example, quantum cryptography, quantum computation, and for quantum computation, it might be one of the resources that could potentially help us to achieve quantum advantage in quantum computations. Yeah. So, and it is so this inseparability of the two qubit states into a canonical product of two single qubit states induces many interesting like quantum phenomena that has no classical counterparts. And we will see in the next sections of like what will be the quantum phenomenon that's based on quantum entanglements. Yeah, this comes to the last part of our lectures, which on quantum teleportation. Before I go into the details of it, I want to okay. So let's compare. So let's introduce let's see how let's compare how we transmit classical and quantum informations. Can we, for in classical world, basically, if you want to transmit classical information, for example, you could just place, if you want to transmit, you want to send a text to your friends, then you just need to click Control C followed by Control V in your keyboard, and you'll copy the text from, for example, Google to Facebook, and then you just click the same link to click send to send the text. Or you could also like photocopy a document and pass it to your friends without any issues. Yeah. So to put simply, basically you could like just use this like X row operation to copy the classical information into two. Yeah. So basically, it just correspond to your photocopying documents, and this basically just words for photocopying machines. Can you do the same thing for quantum systems? Yeah. Or put it simply, can you copy an unknown quantum states by replicating it on a blank quantum state 0? Yeah. So we have to study it in details in order to understand the principle behind it. Yeah. So why we are interested on this is because all the quantum information actually is storing in the quantum states. Yeah. If you want to copy a quantum informations, that means you have to copy a quantum state, and later you see that actually quantum mechanics forbid this kind of machines to be occur. And this kind of machine, because here we are having the this copying machines, quantum Xerox machines, is a quantum operations, and therefore it could be described by it has a metric representation U, and the actions of this quantum operation is just copying this quantum state to a blank quantum state, and what you get is the two copies of the quantum state out of the device. Yeah. Okay, so this U has to be unitary because you are performing some unitary operation, unitary evaluation of this guy, of this state, of the state. Yeah. So to show the restriction that imposed by quantum mechanics, we first input like two different quantum states, psi and phi, into the device. Then what you get out of device is two copies of phi and two copy of psi. Then we multiply the second equations with the Hermitian conjugate of the first equation, sorry. Yeah, then this is what you get. Basically, this part will come from here, this is coming from here, this is coming from here, and this is coming from here. So this U is a unitary. That means like it need to be identity, and what you get is this guy. Then we find the inner products between these two quantum states. So the first part meet with the first part, the second part meet with the second part, and the same for the the right hand side of the equations. This 0, basically give us 1 because it's inner product of the same state. So at the end, what we have here is these equations. Yeah. So for these equations to hold, the inner product of between psi and phi need to be equal to 0 or 1. This means that like phi has to be a quantum state that is orthogonal to phi or identical to psi, which is not true for every choice of quantum states. Yeah. So basically what this tells us is that quantum mechanics like allow us to create a quantum device that copy quantum states and those quantum states that are orthogonal to it, but not to clone a general quantum states. But this actually pointless because like it's not worth the effort to do it, just create a machine that can copy a limited number of quantum states. For qubit system, actually there are infinite number of orthogonal bases, but each of those only consists of 2 quantum states. Yeah. So basically, you create a machine that could only copy 2 quantum states that is orthogonal to each other or identical to it for a qubit systems. Yeah. So a direct consequences of this non-cloning theorem is that we cannot copy arbitrary quantum state and send them to other party. This is inconvenient because if you want to share quantum informations, if we want to share a classical information, basically we just copy and then we send it through in internet, but we couldn't do it in quantum in the quantum world. Yeah. So basically, the way to copy or transmitting the quantum information is very different in classical worlds and in quantum world. Yeah. But this constraint, they highlight the importance of quantum teleportations. So the quantum teleportation protocol can be divided into three parts. First, the sender is Alice. Alice want to send a qubit, this red circle, to Bob, and then Alice and Bob basically share like Bell state is entangled photons. Then Alice, if so, one they have all the resources, and Alice has prepared the quantum state, this red circle. Then Alice just measures her qubits in certain bases and send the measurement outcome to Bob. So this is the measurement outcome, the classical signals. Once both have received Alice measurement outcome, then Bob will just like perform quantum operations on his qubit conditioning on Alice outcome. Yeah. So this is a bit abstract because we don't really know what is happening and why, like, if we have the entangled photons, then we could like send a quantum state. So now we will be going into some mathematical details. So for part one, for the first part of protocol, at least want to send a qubit if with quantum states psi A prime, which have this form, and Alice and Bob share a Bell state, which just that we have introduced before. Yeah. So the joint quantum states of this system can be described is this. So basically, I just like expand this term like by putting this in and putting this into here. By doing some math, right, we could like show that this expression actually is equal to this. Yeah. So I do not show the math here because there's no time to cover everything. But there are two important points that I want to emphasize here. First, you can see that this are different Bell states which has these forms, and you could like kind of compare it against the plus and minus states. So plus is a linear like 1 over square root 2, 0 plus 1 over square root 2, 1. And minus is 1 over square root 2, 0, and minus 1 over square root 2, 1. Yeah, so this is similar. And then like Clyde had mentioned that we could express there as a superposition of like 0 could be 0, 0 cat can be expressed, 0 and 1 can be expressed as a superposition of plus and minuses and the other way around. Yeah, so the trick to go from this line to this line, right, is to express the computation basis in terms of this Bell basis. And there's an exercise for you to verify this. Yeah, and so the second part is that after you like plug in all like this equation, like the rearrange equations in this equation, right? Then basically you could see there's like a lot of terms going on, and then one of the good things about principles of superposition is that it allows you to rearrange the terms without like changing the physics. And so if you compare with Lin's examples on the interference, right, then you could see that like why we get 100% like outcome for the up states, like up path, is because of the cancellations of the positive and minus negative signs. Yeah. So this linear superposition allowed the cancellations or interference to be happens. So here there's no interference here, but what I want to emphasize here is that we could rearrange and then group the terms based on this Bell basis. Yeah. And then if you compare it with this, the original state that at least want to send to Bob, right? Basically, you can see that for for the first one, basically we already have this identical expressions, and for the other three scenarios, basically there is kind of identical. So, but it requires some operation to transform this state to this quantum state. Yeah. So for second part of the protocols, at least you measure a qubit, the first two qubits, on bound basis, this one, and send Bob's her measurement outcomes. Yeah. So this is the quantum state I copied in previous slide. So at least measurement outcome will be like 20% of getting this 5 plus, and both state will collapse to this. Then if at least there's a 25% of at least getting 50, then that get this, and so on and so forth. Yeah. So for so basically you could see that the quantum states of Bob's quantum states basically depends on Alice measurement outcomes. But before Alice sends her measurements to Bob, basically even if Alice performed the measurements on her side, perform the measurement on her side, the Bob qubits still appear to be random from his perspective. So in order for Bob to make some informed decisions to transform the state, Alice has to send her measurement outcome to Bob. Yeah. Otherwise, this protocol wouldn't work. So once Bob has received Alice's outcome, then it comes to the part 3 of the protocol. He could like perform the quantum operation on his qubit conditionings on Alice's outcome. If Alice's outcome is like this Bell state, then Bob does nothing because the quantum state on his side is already identical to the quantum state that Alice wants to send. Yeah. So if Alice sends this outcome to Bob, then Bob apply these exact operations. And if Alice outcome is this, then Bob apply the X operations. And the last one, if Alice get this, then Bob apply XX operations on his qubit. So we can see that the final states of both qubits is basically identical to the qubit, the quantum state of qubit that Alice want to send. So yeah, so now so this will be the end of the protocol, and we can see that Alice has sent the quantum states without knowing like without just performing Bell's measurements, and both you have to do some operations conditionings on Alice measurements. Yeah, interestingly, even after all of this protocol, right, Alice and Bob still have no knowledge on the value of A and B. That Alice only performs Bell measurements on qubits and send the respective measurements outcome to Bob's, while Bob's perform a unitary operation conditioning on Alice measurement outcomes. Yeah, so all of these operations actually don't really reveal the informations about A and B. So this all of the protocol could be done without any loadage of A and B. Yeah, so this is very interesting. Yeah. So you might like have you might kind of curious if whether Alice and Bob have violated the non-cloning theorem. Actually, no, they didn't, because the original copy of the original copies of the quantum states actually is completely destroyed right after the Bell measurements, because after the Bell measurements what Alice possesses is just the Bell states, and if she didn't compare the measurable outcome of these two quantum systems, basically this qubit will appear to be random from her perspective. Yeah. So in this protocol, basically only one copy of this appears, and after the protocol, this copy is transmitted to both sides. Yeah, yeah. So this could be, so this protocol could be nicely summarized in this equations. Not really equations, just a statement. So quantum computation, quantum teleportation could be done using two classical bits and one entanglement. These two classical bits is the it contains the information about Alice measurement outcome, and the shared entanglements is the entanglements in the Bell states. And this allows us to transmit one qubit from one side to the others. Yeah, actually the naming of quantum teleportations might be misleading because like no quantum system is physically transported from one place to another in the protocol. It is the quantum information that's stored in the form of quantum state being transmitted from one quantum state to another, one quantum system to another quantum systems. Yeah. So this will conclude the whole protocol. Yeah. And to summarize, in this lectures, basically, we have learned that how to describe the two qubit quantum states using the tensor product, canonical product structures. Then how do we apply the Bond's rule to these two qubit quantum states? Then we learn how to combine single qubit quantum operations using using the canonical products and acting quantum operations on the quantum states, on two qubit quantum states. Yeah. Then for the first two are the basics. Then the third part of the lectures is we go into mathematical details of quantum entanglements, and we see that actually there are two distinct classes. That one is called a separated quantum state, the other one is entangled quantum states. For entangled quantum states, it contains quantum entanglements and the measurements on one part of the system will affect the affect the other systems. While for separate quantum states, basically like the measurements on each of this each of the each part of the system wouldn't affect each others unless you are using like entangle operation and stuff. Yeah. And we kind of learn how to use a simple way to distinguish entangle and separable states. Then before going to quantum teleportations, we went into no cloning theorems and see the like distinctions between like copying quantum informations and classical informations. And we say that like quantum mechanics imposes some constraints on how we copy quantum states or quantum informations. And this kind of could be could be bypassed by using two bits of classical informations, two classical bits, and one share entanglements. And then this allows us to transmit quantum states without knowing what are the states that we want to transmit. Yeah. So that's all for my lectures, and thanks for your time.